Our next speaker is Dr Rachel Capon from the Mineral Products Association, and she's going to weave a bit of magic. And the magic of that is how carbon CO2 can be absorbed by concrete through the carbonation process. I think this is a very exciting benefit of concrete that has been overlooked in the past. And Rachel's going to explain forward a UK first, which I always like to hear about at conference, and that's the development of a new tool that can help us assess the carbonation potential of concrete pavements. Rachel.
Okay, thank you very much, Steve. I'm Rachel Capon. As Steve said, I'm from the Mineral Products Association, and we're the UK Trade Association for the aggregates, asphalt, cement, concrete, dimension stone, lime, mortar, and industrial sand industries. I'm the Sustainability Programme Coordinator for UK Concrete. I did work in the cement team. Prior to working in the concrete team, and I'd just like to acknowledge the other partners in this project. So alongside MPA, we had Ricardo, Heriot-Watt University, Leading Edge, which is a market consultancy, and also the Concrete Society. So just going back to cement manufacture, you might already know this, but we'll have a review in case you don't. Cement's a man-made powder and that is used as the binder in concrete when you mix it with water and aggregates. And the cement making process can be divided into two basic steps. So the first is making clinker in the kiln. That's at very high temperatures, about 1,450 degrees Celsius. And as part of that process, the limestone that is your raw material decomposes into free lime and carbon dioxide. This is the calcination reaction. So this is your calcium carbonate and your limestone or chalk decomposing into calcium oxide and CO2. And this is the key reaction in making cement, or making cement clinker. So what you get out of coming out of the kiln is something called cement clinker, and then that's ground with other materials to produce Portland cement. And if we look at the carbon dioxide emissions from cement production in the UK, so from cement production, there are then two sources of carbon dioxide emissions. One is because you are burning fuels, so historically coal, but now increasingly fuels, waste-derived fuels derived from household waste and other waste sources. So that's about a third of the CO2 emissions that we get from cement manufacture. But the calcination emissions from the reaction of the limestone decomposing, that's about 2/3 of the total emissions from cement production, and it's actually increasing as the fuel burning becomes more efficient. So these are the two sources of carbon dioxide emissions when you make cement. They're reported in two different categories in the National Greenhouse Gas Inventory Report, or the NER. So the fuel emissions go in one category, which is 1A2F, which is all to do with burning fuels, and then the calcination emissions go in this other category, 2A1, and category 2 is all to do with industrial processes. Okay, so if we think about recarbonation of concrete, or sometimes we just call it carbonation, it's the naturally occurring reversal of the calcination reaction. So once you have included the cement in the concrete as the binder in the concrete will start to reabsorb the CO2. That reaction effectively reverses. This is scientifically well established. And the other thing to note is that it's actually a permanent carbon sink. So that CO2 is reabsorbed by the concrete and locked into the concrete, and the concrete is effectively becoming more stone-like. there's an established industry methodology for calculating the CO2 sink from carbonation in environmental product declarations and in life cycle assessment, and that's given in the British Standard EN 16757, the product category rules for EPDs for concrete and concrete elements. Carbonation has also been recognised by the IPCC in their 6th assessment report, which came out a couple of years ago. But there isn't yet methodological guidance which tells countries how to include it in their national greenhouse gas inventory reporting. But this is something that the industry has been working on for 10 years now. And in 2018, IVL, who are the Swedish environmental research industry, published a report with outlining a calculation methodology which would be IPCC compliant. And in the IPCC, you can have 3 different tiers of increasing complexity of calculation. So this report also included 3 tiers of increasing complexity. As well, I'm talking about recarbonation. I'll go over here without making a shadow. So these are some test cubes from the University of Dundee, which I'll come back to later. But this shows the commonly performed test to see how carbonation is progressing. It's called the phenylphthalein test. So you cut your concrete. These samples are all about 18 years old, and then you apply phenylphthalein. It's pink in the middle, which is where the area that is not carbonated, because that's still alkaline. You can see that the carbonation has come in from the edge. So the area where the indicator is no longer pink is where the carbon dioxide has penetrated into the concrete and made it acidic. So that's the area that is carbonated. And you can see these are all different types of concrete, and the area that is carbonated is different in each of them. Okay, so under the Kyoto Protocol, Annex 1 parties, which are basically developed countries, including the UK, we have to report all our greenhouse gas emissions from all sectors, our annual greenhouse gas emissions, to the United Nations Framework on Climate Change. And the report includes greenhouse gas emissions from cement manufacture. It also includes greenhouse gas emissions from other sectors. So one of the sectors is land use change and forestry. And importantly, at the moment, this is the only sector that is actually reporting a sink rather than emissions. So land use and forestry is the only sink counted at the moment. But recarbonation of concrete is also a sink, and as I've already said, it was considered but not included in the 2019 update of the IPCC reporting guidelines. But in 2018, IVL published a calculation method for carbonation. It was developed in collaboration with industry, so with the European and global and American trade associations. IVL are also the inventory agency for Sweden, so they're responsible for compiling the whole greenhouse gas inventory for Sweden, and Ricardo plays the same role in the UK. So in Sweden, they included the Tier 1 calculation of the carbonation sink as a memo item in their national inventory report in 2020, and the sink that they calculated for 2018 was 297 kilotons of CO2. Now, looking towards including recarbonation in the UK National Greenhouse Gas Inventory Report, once the IVL report had been published, MPA approached BEIS, as it was then, it's now DESNZ, who are responsible for the UK Greenhouse Gas Inventory. We hosted a workshop in July 2019 with BEIS and other UK government officials. Ricardo, who are the UK Inventory Agency, IVL, Sweden and Denmark, who are countries who've done work on carbonation modelling, and also our European and international trade associations, SEMBURO and GCCA. So the greenhouse gas inventory at BEIS were very keen to test the IVL methodology, but they were also very keen to have a tier 2 calculation, which is more complex than tier 1, so that they will build upon rather than duplicate work that had been done internationally. They tendered this work in summer 2021, and we were successful in winning it. So we led a consortium which critically included Ricardo, the inventory agency, and we also had other contributors to the consortium. So what does the IVL methodology say? Well, the tier 1 methodology is a very simple calculation. It's based on an international literature review, and different literature had actually quite different values. But the carbonation sink is calculated as 23% of the calcination CO2 emissions for all the cement clinker consumed nationally in the reporting year. So it's based on the consumption of cement rather than the production of cement, which is quite important because in the UK we do import 20 or 25% of our cement. And as I've said, so this was reported by Sweden in their 2020 inventory report. The tier 2 methodology is a more complex calculation. You calculate the carbonation sink by considering different concrete applications. You need the annual cement consumption data to make sure your overall concrete consumption is correct. And then you look at the concrete that's in primary use. You need to divide it into at least 5 different applications, which cover at least 65% of national cement consumption. For each of your applications, you calculate what's called an emission sink factor, and that uses the EN 16757 methodology. And we also use something that's called the onward calculation method. Basically, that means that we assume that the sink is instantaneous, although it's not. And then the tier 2 methodology also considers the concrete entering the end of life and secondary use, but it just gives basically a ballpark figure for a CEM 1 concrete, which is 10 to 30 kilograms of CO2 per meter cubed of concrete. Tier 3 methodology, there's not a lot of detail about what a tier 3 methodology would look like in the IVL report, apart from that it would be a more advanced software model, because basically you'll be disaggregating your concrete use data even further, and also disaggregating the annual use further. Okay, so these are the stages that we went through to develop the tier 2 model. So we had a literature review by Dr. Phil Renforth of Heriot-Watt University. We also looked at the UK data sources that were available. The key part of building the model was looking at the model elements, so identifying annual activity data to import into the model for the primary use and the end of life and secondary use of concrete, and identify appropriate applications and calculate the concrete emission sink factor for each application. And then also what was recommended by the literature review was that although it was appropriate to use the EN 16757 methodology for the primary use concrete applications, the 10 to 30 kilograms of CO2 uptake suggested by IVL for the secondary use and end of life concrete was not sufficiently robust for the UK tier 2 model, so that we should calculate a UK specific carbon sink for concrete entering the end of life and secondary life stages. We also carry out some model validation and quality assessment, quality control. We were helped greatly by Ricardo in that, because they're inventory experts, and they understand the requirements. So we compared it with the experimental carbonation data from Dundee that I've shown you, and Ricardo also carried out an uncertainty analysis for us, which is an important part of the reporting to the UNFCCC, and we made recommendations for future work. The final project report has now been published by DESNZ. So we looked at what data is available for concrete in primary use. So on the left here, we've got top-down data. So MPA collects a lot of industry data. We collect data on cement consumption and cement sales by product type. There are also available sources of bottom-up data. The key one here is the ONS construction output, which is also broken down by sector. There's commercial contract data available from a couple of commercial sources, and this bar actually feeds into the ONS construction output. And then there's also sector-specific data. So, for example, from the NHBC, or from IPA, or from National Highways, or Scottish Transport. Looking at this, we decided for the level of granularity we were looking at in this model, the most appropriate data to use for the annual activity data was this top-down data from MPA in terms of cement consumption and cement sales by product type, and the ONS construction output broken down by sector. That does leave data gaps, and particularly we needed to relate the ONS construction output by sector, which is an economic cost output, to the cement sales, which are in terms of tonnage. Okay, so we chose, our expert opinion of structural engineers from within MPA. We've broken down the market into 5 different primary use concrete applications. So the first one is composite frame buildings. As you can see here, this is steel frame with a metal deck and concrete on top. So this construction is typically used in commercial buildings and offices. Concrete frame buildings. Here, a reinforced in situ concrete flat slab with columns. That's used in high-rise residential buildings and in hospitals because of its fire and acoustic performance. We looked at masonry buildings, so most but not all of the houses being constructed in the UK, and also low-rise apartment blocks are still of a masonry typology. So you can see the inner leaf of the external walls here is concrete block and an external brick leaf. The full type with infrastructure projects, so that includes energy, rail and roads, and then mortar and merchant sales. So we know how much factory-made mortar and bagged cement we sell. So the activity data sources for these different applications, numbers 1 to 4 all come from the ONS construction output, and we've developed proxies to relate that to concrete consumption. Number 5, the mortar and merchant sales actually comes from our top-down MPA data. Okay, this is how we calculate the emissions factor. I don't want to overwhelm you with maths, but we follow the methodology in Annex G of EN 16757. It used to be Annex BB, but in the latest update last year, it's now Annex G. The calculation hasn't changed. So we know how much CO2 uptake we can get per kilogram of cement, CEM1. We know how the carbonation progresses with the square root of time, and we can calculate the CO2 uptake per metre squared of the concrete surface. If we've got some SCMs in the mix, then the carbonation front progresses a little bit more rapidly. And we have these lookup tables in the standard. So you can see that as the strength increases, this is the K factor. So that tells you how quickly the carbonation is moving through the concrete from the surface. And you can see that it gets lower as the strength increases. It also depends on your exposure. So if you're outside an exposed terrain, it's lower. If you're sheltered from the rain, it's higher. And it's much lower if the concrete is buried in the ground. The other difference to notice is this is a variable called DC, which is a degree of carbonation. So K is telling us how far the carbonation has moved through the concrete. DC is telling us how much of the CO2, which, the theoretical maximum CO2, which could be absorbed when the reaction, is being reversed, is actually absorbed. So the key thing to note is that for outdoor structures, it's high. It's 75 or 85% of the theoretical maximum. But for indoor structures, so inside buildings, it's only 40%. That's to do with the differences in relative humidity. Okay, this is adjustments for SCMs. So I'll move through these quite quickly, but this just shows how we calculated the emission sink factor for each of the applications. So we've got the composite frame office. So here's your concrete. The bottom side is not exposed to air at all because it's on a metal deck. But on the top side, you actually have a raised floor, so that the top side is exposed to the air and will carbonate. Okay, this is our concrete frame residential building. Again, we've got a typical prototype, 6-story apartment block. And we look at which surfaces will carbonate. In this case, it's actually the underside of each slab, because you have a ceiling, typically have a ceiling void, and also the core. We use the same prototype for masonry and for mortar. So we're just looking at a typical two-bed, 2-story mid-terrace house. So you're getting carbonation in the lightweight aggregate blocks in the walls, but also in the beam and block ground floor, in the strip foundations, in the roof tiles. And then for the mortar and merchant sales, we look at the mortar that's in the party walls and the cavity walls. The masonry absorbs CO2 much more quickly and also the mortar because it's lower strength, so much more porous. Finally, we get onto infrastructure. This is actually 20% of the total construction output in the ONS statistics, so 20% by value. It's actually a very diverse sector because the concrete is going into rail or to energy or to roads certainly in terms of economic output rather than the concrete. In economic construction output, these are similar in value. The difference is that rail and energy tend to be very large projects like HS2 or Hinkley, whereas for roads, there's a much greater variation in the projects. Anyway, within the limited time scale of the projects we were doing and the scope, we decided that we would use a typical concrete slip form barrier as the prototype for our emissions sink factor. And that's using a CEM1 concrete with 300 kilograms of CEM1 per meter cubed of concrete, and we get an emissions sink factor over its lifetime, which will be 5.65 kilograms of CO2 per meter cubed of concrete. So these are the parameters that we end up putting that we've put into the model. And no, actually, the other thing is, so we've got all these applications. We also use our cement production data from MPA to make sure that the top-down and the bottom-up concrete values are consistent. This is just a comparison of some of the emission sink factors that we've calculated for these UK-specific applications against examples that are in the annex to EN 16757 from Sweden. So you can see the first two are for residential, and then here we've got the factor of 5.65 that we've calculated for our slip-form road barrier. You compare that to a portal frame bridge in Sweden, actually had a very high cement content, 400 kilograms CEM1 per meter cubed of concrete, and that had a slightly higher emission sink factor of 6.9 kilograms of CO2 per meter cubed of concrete. So these are the Dundee test samples. Again, these are about 18 years old. We also had some test cubes at BRE that are about 2 years old. So we looked, or Dundee did it for us, but looked at the tested and found how far the carbonation had progressed through the concrete. What we found is that the progression of the carbonation through the concrete agrees with the factors in EN 16757 if it's a normal strength concrete, so if it's less than 14 megapascals and it's a CEM1 concrete. The agreement was not as good for concretes that are higher strength and or have higher SCM content, and that's quite important for infrastructure because projects like HS2 and Hinkley are actually using very high proportions of GBS and at very high strengths. Okay, moving on to end of life and secondary use. So we spoke to the National Federation of Demolition Contractors, and we know that about 95% of concrete at the end of life is processed and reused. So it'll be crushed and reused either on-site or taken off-site. So we're using construction and demolition waste statistics from DEFRA, and we assume that the concrete fraction in that demolition waste is 59%. We assume that all the demolished concrete is coming from commercial buildings built in the last 30 to 60 years. Of that, 60% is high-strength concrete, so only the surface layer will be carbonated. 40% is low-strength concrete, which will have completely carbonated. And the concrete is crushed either on-site or off-site for reuse, either in groundworks or in an unbound road brace. And the factor we calculated for carbonation during the secondary life is 39.41 kilograms of CO2 per meter cubed of waste concrete. So you can see this is quite a lot of carbonation actually occurs during the secondary life for high-strength concrete. So this is the overall emission sink we calculated for 2020. So 1.548 megatons of CO2. The uncertainty we calculated was plus or minus 34%. Of this 1.548.86 is from concrete in primary use, 0.686 megatons is from concrete at end of life and in secondary use. We can compare that to the total UK greenhouse gas emissions, it's about 0.4%. And if we compare it to our cement consumptions, it's about 31% of the calcination emissions from our cement consumption is reabsorbed by carbonation each year. Of that, so 17% is from concrete in primary use. So that's consistent with what IVL recommended at Tier 1, which was 20%, so it's quite consistent. And also we showed that the emissions sink factors we've calculated for the UK are comparable with the examples in EN 16757. 14% is from the concrete at the end of life and in secondary use. This is higher than the figure given in the IVL methodology. It's below the maximum that it could be, which is about 110 kilograms CO2 per metre cube concrete. And we think that it's consistent because the UK market is mature and that we do have much higher recovery and recycling rates than other countries. This is the model output, which I don't expect you to be able to read, but you can look at later. So just to say that the final project report has now been published. We always recognise that this was a UK first and the first time that a Tier 2 model had been done. So there are many recommendations for future work and future improvements. And we're now discussing including this in the next UK National Inventory Report submission with DESNES. It wouldn't count towards the main numbers in the first instance. It would go as a memo item in an annex. Thank you.
Thank you, Rachel. Any questions? Right at the back there, thank you.
Philip Dumelow, as a materials engineer, carbonation of concrete is the last thing I want to see. We design mixes specifically so that it resists penetration by environmental gases that can damage the concrete. But I'm particularly thinking of carbonic acid. I have had the experience in my days with a local authority when I had to do an investigation on a multi-storey car park where palings were spalling and dropping off, and with a drill and a spray bottle of phenolphthalein, I discovered that they'd carbonated all the way through to the rebar, which was being attacked, rusting, expanding, and causing the palings to spall. They all had to be replaced with steel, which was not very environmentally friendly. What's your comment on that, Rachel, please?
I agree absolutely that recarbonation has been a problem historically, and we're not trying to encourage it. And current design codes would prevent it. I'm not a structural engineer, by the way. I'm not an engineer. I'm a mathematician originally. Our aim is where carbonation does occur to get it accurately accounted for, and that would include in the National Greenhouse Gas Inventory and in environmental product declarations where it is already accounted for in many of them.
Any other questions, please? Sorry about leaving you over here. Thank you.
Thank you. Paul Cole, Skanska. It's a question that I think, because you've got a lot of detail in there, and we do a lot of piling within Skanska, so you've got 30-metre long piles. I fail to see how that can carbonate at the depths in the same way that an entirely exposed building concrete can. And for a volume of concrete, one element might have a very different surface area to another. So in your calculations, you're looking at area, but you're also comparing it to an overall volume use of concrete in the industry. I mean, that you're a mathematician, but that to me sounds like an almost impossible calculation.
It's a pragmatic calculation, and certainly, so for the building prototypes that I showed you very quickly, we counted also carbonation on the piles, which is much lower than the carbonation in the superstructure because they're in the ground, and part of the piles we assume will be below the groundwater level. So there is much less carbonation under those conditions.
Thank you. Sorry, we won't dwell on it. We can perhaps have a conversation about it later. But you can't have sampled piles 30 metres below the ground to see how they have carbonated. So, and your concrete blocks with the phenolphthalein test, they're a small volume of concrete with all sides exposed. So measuring the condition of the carbonation within that situation is going to be very different to many other types of environments we get in the infrastructure environment in the real world. Yeah.
Oh, I agree. So obviously the experimental data that I've shown you is a small sample, and most of the methodology was based on larger samples, probably from Sweden, that were included in EN 16757. But it's also an area that was highlighted in the literature review and that we've highlighted for future work, that the phenolphthalein test, it shows you, it's relatively accurate at showing you how far the carbonation has progressed. What is less certain is how much CO2 is actually been absorbed, what percentage of the theoretical maximum has been absorbed in the volume that has carbonated.
Okay, sorry, one last question.
Hi, Joe Paulson at ACOM. I'm just trying to understand the angle of the MPA and BASE, as they were known. What are they trying to achieve with this type of report? Because it just seems like a bit of greenwashing to me, to be honest.
No, it's not greenwashing, because the carbonation is already happening. We know that, and we've already heard from the first question that it's already happening. What we are trying to achieve is an accurate as possible estimate of how much is occurring nationally each year, so that it can be included as a sink in the greenhouse gas inventory, and also can inform other carbon budgets and targets. And also, you know, there are also other countries who are interested in learning about this methodology.
I'm afraid I'm going to have to call a stop the question due to time, but if you do have any further questions.
Yes?